Hello everyone, welcome to MLAS 700. We're going to start off with a lab this week that's going to be over in Google Colab. So I actually have it pulled up already, but if you're wondering how to get there, if you open up a screen, if you go to Google and you just type in Google Colab like this, you can come in here and just get started that way. And once you just click on this link, you'll come over here. You just create. If you've got a Google account, it should just get you set up, and you'll be ready to go. It's a Jupyter notebook environment, if you're familiar with Jupyter notebooks. But this is what we'll use for our intro lab today, and this will help to explain the linear regression that we're going to run through. We're actually going to be using the scikit. This is pretty straightforward. There's a scikit example. When I say scikit, I'm saying the scikit learn. And there's a linear regression model right here that they've got out there. I'm just going to walk you through their model, and so I'll type it out. I'll bring it over, but they have tons of examples here that are all just fantastic, and go through quite a bit of. It's a very robust, comprehensive machine learning framework. So this is a great way to learn, not just learn, but also develop scientifically usable machine learning models for publications, actually also for industrial uses. There's a lot of different capabilities here and that you can explore. Okay, so I'm going to head back over to Google Colab. I'm just letting you know that scikit is a library that we will be using to work through this lab today. All right, well, let's go ahead and get started on this. The first thing we're going to do is we're going to get our library set up, and this is again, we're using a different programming language. This is Python. This isn't simplified C. This isn't the Arduino programming language. This isn't the APL, which is a simplified C that is on Arduino. This is Python, so it's different, and the syntax is going to look different. But again, we're doing this because it's so much easier to explain it here. There's more tools available to us, and the libraries are pretty quick and easy to work with. So we're going to import matplot live.pyplot as PLT, and then we are going to use that import numpy as NP, so that's good. We don't need Seaborn. These are pretty standard, but we don't need those. And then from sklearn import, we are going to import all of that. So that is correct. From sklearn import data sets, linear model. From sklearn metrics, import mean square error and R2 square. So remember, this right here, this is used for eval, model eval. And then this here is the actual machine learning model, actual ML model. Okay. And then we're gonna load our data set. And in this case, we're going to be using the diabetes data set, and it kind of knows exactly what we're doing here. It's pretty good. It's not too bad. So that's correct. We are going to be using this data sets, this right here, datasets.load diabetes. We are going to be using that. But we're going to be creating, remember, we have to have an X and a Y. Right, so so that's when we create the data set, we're going to actually return an X and a Y. So we're going to do diabetes X, and then we're going to do diabetes and then we're going to return x and y equal true. So in other words, I want to return, and I'm going to take the data set here, and then what I'm going to do is I'm going to pass it to two variables and split it up automatically. That's what the return x y equal true, meaning that I want you to return it in an xy format. Okay, and I think that's all I need there. Okay, then we're going to do down select to one feature, which is just going to be the diabetes X. We're going to we'll explain more about what's happening here after we show off what we're doing, but we're gonna just create one feature. So use only one feature, and then that's going to be diabetes X. Yep, that's exactly right. So the AI that is here knows what's going on, and some of this is because also this is a pretty standardized training. When I say training, I'm not talking about machine learning. I'm talking about human learning. So in this case, this is for human training purposes. This is a pretty common data set, especially when we're talking about training you on how to use and do machine learning in Python. Okay, so that's all correct. Everything looks good there. And then what we're going to do next is we're going to split the data up. Split the data into train, test, sets. Okay, and then that is correct. Diabetes X train equal to yep, that's correct. So all right. And then what we're going to do is we're going to split up the targets into training. We're going to split up the Y side of it. So I want to split that. That was the X side, and so let's do split the data into train, test, sets, Y. Let's put up here X. Okay, oops. And that's what we want, diabetes Y train, and then that is correct. And then we're going to do a create linear regression object, and then that is all correct as well. Reg R equal to linear model.linear regression, perfect. That's also correct because we want to train the model using the training sets. Reg, we're going to fit the model, diabetes X train with diabetes Y train, correct. So that is all correct. This is what's great about this is, it used to be we had to type all this out by hand, and now we've got an AI that helps us. There's an AI on the back end of this that's helping us to predict what it is that I want to do next, and it's saving me a ton of time. So this is cool. Okay, so next up we're going to do a prediction. Prediction using the test train. And using test train set. Okay. Diabetes Y pred, reg R predict diabetes X test, correct. Oh, nope. Let's see if am I going to get that back? Yes. Okay. Then, so that's all correct. And then what I'm going to do now is we're going to go into the model evaluation portion of this. Model eval, show COEFFICIENTS, coefficients, show coefficients. We're going to do a print, print coefficients with a regular expression /n reg r co f, correct. And then the mean squared error, that is also correct. Y test, Y pred, and I think that's good. I think we're good. I'm good with that too. Yeah, that's cool. Print coefficient of determination, R2 score, correct. Yeah, we want that too. Okay. All right. So then now let's, we want to plot the output. Plot the output. And then this is a plot scatter diabetes X test. X-Tix plot show. That is correct. All of that's correct. So that was what is amazing. It filled it in, did it what we need to do, did what we need to do, and then I'm going to go ahead and push play. I think this is going to go through on the first run through here. Used to get debug issues, all kinds of problems, but this is pretty standard code, and you can find this code out in Scikit. I want to run through it with you like this because it's nice to be able to see the code developed in real time and then the code explained in real time as well. Okay, so here's our output. And this is great because I got a coefficient of 938. I got a mean squared error of 2548.07 with a coefficient of determination of 0.47. That's the R-square value, the 0.47. We don't have a lot of data here. You know, if you look at the points here, there's not a lot of points. That's something that we've got to, you know, we can go and, you know, I mean, how many samples we've got. We can do an n sample count, but we can do a quick count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we got 20. It's not a lot to work with, but it's enough to give us some kind of line of fit. It's enough to give us a prediction that's somewhat useful, but how do you know if it's useful? So the coefficient of determination is kind of iffy. It being at 0.47 is right on the line of being iffy. So remember, this is where we go into model evaluation. So let's pull up. I'm going to pull up our lecture, and I'm going to pull this in. Okay. So remember, what we're doing here is we're doing this right here. We're taking the dependent variable y, and then we're trying to find out given an x, what's a y, and so this x is the independent variable here. So given our x's, give me a y. So and then we're going through, and then where's my right here. Okay, so we're going to take a coefficient of determination. Remember, when we were looking back at our lecture, we want a low MSE score, and then we want a high R score. So, or an R square, or coefficient of determination needs to be higher. So that's what we're looking for here. So we're not sure because coefficient of determination is 0.47. It's in the middle. But then that means that this might be usable if this is really low. In other words, our mean squared error. So you really don't know. It looks super high in comparison to this. So you might think, oh, the mean square error is telling me that this is not a usable model. It actually, we don't know that yet because we got to do a little bit of a model evaluation here. So this is not what you won't find this in the Scikit. The Scikit example, this evaluation piece of it. But this is something that we'll explore, and we're going to be using Gemini to help us evaluate what it is we just built. All right. Okay, so what we're going to do is I'm going to create another code. Oh, no, I already had the code block there. That's okay. I'm going to generate this with AI. I'm going to use Gemini for the next step here. So what I want, because we don't know what the scale dependency is here, we don't know what the scale is as it relates to what the mean squared error is. So I'm going to use Gemini to my advantage. So then this is where this is kind of cool. I'm going to ask it. I'm going to say, can you calculate the scale dependency range of the MSE output. And then it's going to go and create a program for me. Okay. And we'll see if this works. Okay. So we'll run this and see what happens. Okay. So this is okay, yeah. So this plot shows how the MSE changes with different scaling factors applied to the target variable. Observe the range of MSEs to understand the scale dependency. So this is our scale range, right? And so here's what's interesting is the scaling of a factor target variable. This is our scale dependency. It created a graph here, which is actually a little different than what I got last time, which is kind of interesting. I've done this a couple times, and this comes out. Always seems to find a different way to do it. And that's the nature of a large language model. That's, we're dealing with a stochastic engine, right? Which is the same thing as a human brain. It's a stochastic engine. Okay, so the good news is this is our scale So in other words, if you compare our number 2,548 against our scale here, our scale dependency, it's way down here. So in comparison to, being scale dependent, we went and ran a program to compare MSE against our scale, our dependency, and then we can just kind of gauge it. The number that we have for our mean square error is super low on our scale. So it's way down here on the line. So from that perspective, we're okay. So there's not a problem in that regard. So that's a nice evaluation metric for us. And so now what I want to do is I want to create another code segment. I already did that. Here we go, down here. So I want to create another code segment just to compare. Is our coefficient of determination good or bad? And so can you here, hold on, generate with AI. So can you determine if the coefficient of determination, determination, there we go, is good or bad? And then let's see what it does here. Okay, so this is interesting because it gave us some code. It gave us a return as comments, which I really appreciate. So the coefficient of determination is a statistical measure that represents the proportion of the variance for a dependent variable that's explained by an independent variable, or variables in a regression model. It ranges from 0 to 1, so it's standardized. And so the interpretation here is what I'm looking for right here. So perfect prediction, the model explains all the variability. Remember that what I told you earlier, it's that idea of explainable variance, right? So if we have a 1, it means that all the variance in the system is completely explained. That's what that means. A 0 means there's no explainable variance, and those are both bad. So having a 1 means there's probably a problem in the model, and having a 0 also probably means there's a problem in the model. So what we're looking for is something that's in between 0 and 1. So if it's in the middle, so if you're R2, so let's keep reading here. The idea of good, there's no single threshold for good. See, that's actually very intelligent of it to say that, because that is correct. You can have a great R2 value and then a really bad MSE score, and then your model's not good. Conversely, you can have a really bad, you can have a really bad MSE, I'm sorry, a really good MSE, and then you can have a moderately bad, and that's still usable because there might be something explainable and a phenomenon within the data set that is useful because the MSE is so low that there might be something there. So, and it's kind of looking at this diabetes set, it's very similar to that. Even though we're below 0.5 and we've got a 0.47 on an R square, that's not too bad. But it does give us an interpretation of what that looks like. If your R square is 0.5, it explains half of the variability of the dependent variable. This considered moderate, so it's moderately good. So an R2 close to 1 indicates a good fit, while a value close to 0 suggests a poor fit. So we don't have a great fit, and we don't have a bad fit. We have an okay fit. So that's what... But because our MSE is so low and we have an okay fit, it actually means our model's really not too bad. So where I'm going is I want you to hear my narrative. I want you to hear how I'm running through it in my head to do the evaluation. And again, we have a decent one. And you know what you could do to clean this up some more? We collect more data. And that would be that absolutely would give us, and then we rerun we rerun our data, and then rerun our linear regression, and then we redo the model evaluation. That might get us a better predictor of success in this case, or it might get us a better predictor, a better line of fit. Let me put it that way. Now, again, this is there's some limitations to this. One of the biggest problems with a linear regression is it's a single IV and a single DV. It's a single independent variable with a single dependent variable. And what that means is I can't really take into account confounding variables. I can't take into account multivariate situations. In other words, well, I mean, what else could there be? Are there other mitigating factors? Of course, there are always thousands of mitigating factors. There's always thousands of other different factors that are correlative factors. There are so many. I mean, it's rare for us to ever get into a situation where you can just use a linear regression by itself in high-end research, especially now in the age of machine learning. There's just, you almost always have to come into a research and or a business problem with multiple dimensions, multiple dimensions. So, but this is a great way to ease into multivariate analysis, and which is to use a simple linear regression. Okay. So this has been good. I hope you found this helpful. This was a good exercise just to run through simple linear regression. And we're actually going to create, again, we're going to use a linear regression on the Arduino and create a machine learning model on that. And we'll work up to that in our last week of the course. So if you've got any questions, as always, feel free to reach out to me. And we will... see you in the next lab for this week, which is going to turn us back over to the Arduino. I appreciate it, and we'll talk to you later.